Hello. Welcome back to Decaf-Math ASMR. And as usual, a very warm welcome if you are new here. I hope that you are doing very well at this time. But even if you are not feeling or doing very well, I'm very glad that you are here with me right here and right now. And not that you need my permission, but I want you to know that it is okay with me if you're not doing or feeling very well. Okay, that didn't come out quite as I thought it would. But what I mean by that, of course, I want nothing but the best and all of God's blessings for you. But what I mean by that is that it is okay to come as you are. And I'm happy to have you join me right here and right now in this moment. So it's okay if you're doing wonderfully well, horribly not well, somewhere in between. I'm just glad to have you as you are. So we are just going to hang out, relax, do a little bit of math, and it doesn't matter if you're actually learning this stuff or not. As usual, it's a little bit of math, or sometimes a lot of math, and a little bit of relaxation, and maybe even some tingles for some ASMR. So what I've done today is, we're going to try to tackle another requested topic, and I've written out a couple of questions. So one of our friends here in our math nook is studying and preparing for the AP Calculus BC exam. AP Calculus BC exam. And they requested that we take a look at word problems that involve exponential growth and decay, and specifically that involve the form dy dx equals k times y. So don't worry about, memorizing that or anything. We'll do a little bit of whiteboard work with that. But I just thought that we could hang out, take a look at it. Like I said, I've written out 2 typical questions. One for exponential growth, one for decay. And we can take a look at them together. And but before we do the problems, I thought we could do a little bit of whiteboard work, and we can write out that equation, break it down a little bit. I'll give you some tips, and hopefully that'll be a good foundation as we work through the problems. So sometimes I move kind of slowly. Other times with practice, it's just for the sake of practice, so I move a little bit quicker. I hope that you don't mind, and it really doesn't matter actually whether or not you're learning this stuff. Just go at your pace, or you can zone in and out as you please. Maybe this will be just boring enough to help you fall asleep. Either way, I hope that this is filled with relaxation. I'm looking forward to a peaceful moment of just a little diversion. We're gonna have fun with this. There's gonna be no pressure at all, and it doesn't even matter if you love math or hate math or whatever. So I have my little stress, what are these called? Stress squishies? I don't know. Squish. Just squishing away. Squishing away our stress today. going to tackle this and take it step by step. You ready? So feel free to just sit back, sit back, sit back, sit back. Alright, so let's start with the original formula that was mentioned in the topic request. So let's see. So it's dy dx equals k times y. Okay, so this is the general formula that they wanted to take a look at. So what we're going to do is break it down step by step. So we see here that we have a dy dx derivative. When you have a formula in general, it's a good idea to understand what is a function of what. Specifically, when you have a derivative, it can be kind of confusing if you have multiple variables. So what is a function of what? What is a constant? What is a variable? It's a good idea to be able to break down an equation. Okay, so here for this kind of question, we have y is a function of x. Okay, so remember how functions are. X is an input, y is my output, and the function tells us how they are related. So a function of x could be like 3x squared plus 5x. It could be sine x. It could be e to the 2x plus 7. There's lots and lots and lots of functions, and we study them throughout all of our math classes. And so in general, we just have y and x related in this way. This is going to be for single variable calculus, so we just only have a function of x. Okay, so y is a function of x, and we have this equation that tells us that the derivative of that function of x, the derivative of y with respect to x, so this is the first derivative, equals k is a constant. It's not a variable. It's just a placeholder for a constant times y, which is the function of x, so the original function. So this is a constant. Oopsies. Let's see if I can find another marker. Sorry about that. So we have constant. Okay, it's a special constant, and we'll talk about what that is. But k is just a placeholder for a number, and y is going to be our original function. So another way to look at the first derivative is it being the rate of change of my function, the instantaneous rate of change. So really, this question says that we have a rate of change equals constant times my original function. So the first derivative of a function equals a constant times my original function. And we want to be able to solve this for what my function would look like. So actually, if we tried out, let's say y equals 2x, that would not satisfy this equation. And this is a differential equation because it involves a derivative and something to do with my function. And I actually have a special case here where this equation is separable, meaning we have this little trick where we can put all the y terms over here and the dx over here, and we have a trick to directly solving, and sometimes we're not that lucky. So for this kind of differential equation, it's called a separable diff EQ, and so we're going to do a little derivation and get what the general form of y is. But note that in general, if you just had a random function, unless you got super lucky and guessed your way through, most likely it would not solve this, and you can try it yourself. Like, you could try y equals 2x. So the first derivative of 2x would be 2. Is that equal to a constant times my original function 2x? There's no way, right? Because this side would be a constant, the 2, and this side would have an x. So that wouldn't be possible for it to be a constant times 2x. So unfortunately, that is not our answer, but we will solve this, and we will take a look at the family of functions where we will have a solution. And just because we already know this is going to be about exponential growth and decay, you would imagine that it has to do with e to the power of something. So there you go. We will actually do the calculation here in a minute. But before we do that, I wanted to mention a common phrase that you might hear when it comes to this kind of setup. So oftentimes on the AP test, if it's a word problem, you will need some kind of sentence or some kind of hint that we're actually dealing with this kind of question. So we want to be able to set up either this formula or the one that we're about to derive. And a common phrase is to say that the rate of change of something, so it might not look like y or x, and if anything, more often than not, it's actually dt with respect to time, because rates of change with like growth and decay often have to do with time changing. So we're going to actually work this out with dt, but this is the way that the topic was requested, so I thought we would stay consistent first. But a lot of times the way that we kind of get the hint that we're using this equation is to say that the rate of change of, let's say, a population or mass or whatever the function may be. So y, you can change that letter out, but the rate of change of, let's say, the population is directly proportional to the population or to the mass. These both are the phrases in our problems actually, but the concept of directly proportional. Directly proportional tells us it's this k times y. So the rate of change of whatever function is directly proportional to my function, or sometimes it's varies directly, or even if it just says is proportional to something, you can assume that that means directly proportional. So if you saw that, the rate of change of a population varies directly with the population at a particular time or any given time, this would be the setup. The rate of change varies directly. So k is called our constant of proportionality. It is set for, it's just like a general placeholder to show that the rate of change is a constant times my original function, meaning that the part about varying directly or being directly proportional, that just means that if y, or the population or the mass or whatever the original function is, if that doubles, so it gets multiplied by 2, then this also doubles. The rate of change also doubles. If this gets quadrupled, this gets quadrupled. If this gets times 10, this gets times 10, right? So it's directly related, directly proportional, as opposed to the concept of inversely proportional, which we don't have to worry about for these kinds of questions. But inversely proportional would look like this. We still have our constant divided by our function now, and the reason it's inversely proportional is basically if y gets doubled now, then the rate of change, if this were dy dx equals k over y, this would be halved. So if this goes up doubled, then this would be halved. If this were quadrupled, this would be quartered. So it's inversely proportional. This is all for multiplication, right? And then of course there are times where things aren't related at all in any way, but you could have inversely proportional to the square of something, and there's applications of this in chemistry and I'm sure other situations, but the one that we want to focus on for this is directly proportional, and specifically the rate of change of something being directly proportional to the original thing at any particular given time. Remember, we have y as a function of x or t or whatever. Okay, so I just wanted to point out this wording if you haven't heard it before, but this concept pops up also on the SAT, the math part of the SAT, so it's good to know, and I'm sure we'll come back and do some problems related to this, but maybe not in this context. Okay, so now what we're going to do, so when I say a constant, I mean that it's the constant of proportionality for this particular question. So, pi or e is like a universal constant. I don't mean that for k here. I just mean that it is the constant of proportionality for our given question or problem. Okay, so now we can solve this just because it's separable and we can mess around with it to get a general form and a general family of formulas that might be helpful to memorize for these kinds of questions, but if not, at least seeing the steps here could be useful if you want to kind of duplicate them for the test. So let us do that. And in fact, at this point, I'm going to go ahead and switch the x to a t, just because we're talking about growth and decay. I'm just going to slip that in there. But remember, these are just general variables. You can apply whatever you need or prefer for any given problem. You can change up the letters, but just remember the key concepts of y being a function of whatever this variable is, most often time for growth and decay. K is our constant, and again, y is whatever we're talking about. So the general idea for solving this is that we are going to move the y terms over to this side, and this dt can just go over here. K can go wherever it wants because it's a constant, like when we deal with integrals or derivatives. When we take the derivative, we can just pull that out, so we don't really care which side it belongs on, but it's just easier to keep it here, so that's fine. So I'm going to go ahead and move this y over to this side of the equation. Here's an equal sign. And I'm going to do that by dividing. If you're not comfortable with these multiplying, dividing steps, this is a concept from algebra that we've touched on a little bit here on this channel, but don't worry about it. I just want to point you in that direction if you're struggling with this part, but we're going to kind of move through that a little bit here. So to move this y over here, I divide by y on both sides, or since it was a multiplication, k times y, I'm going to do the opposite, divide by y. So I would have dy over y, and at the same time I'm going to move this dt over here by multiplying, so I would have a k dt, like so, because it was a divide. Okay, so when I say that, I'm already kind of cringing because it looks like you're multiplying. Technically, when we find the derivative, we are talking about a limit, and usually if you really, like, dt is not an actual value. Delta, the change in t, is, and so theoretically you're really moving delta t over, and that is technically technically a value, but d, the small differential like that, is actually a limit, and you can't exactly separate that, but you can treat it as though you're multiplying and dividing, though it's that way. But just when you say it out loud, don't say it like that. Just move this y over, move the dt over, okay? So we're going to get all the y terms here, and notice that everything is just multiplied, or in this case divided. And that's exactly what we want, because now we can take the integral on both sides. So we're going to take the integral here and here. So we don't have any like pluses. There's no like dy plus 2. That doesn't work. So this is nice and separable. So now we can just take the integral of both sides. The integral of dy over y. It might be easier to write that as 1 over y dy. And what is the integral of 1 over y with respect to y? Or you can think of it as 1 over x with respect to x. What's the integral of 1 over y? This is one of our basic integrals. Do you remember? In other words, the derivative of what gives me 1 over y, or 1 over x, or 1 over whatever. Exactly, the natural log. Very good. So this is going to be the natural log, and usually you put in an absolute value to be safe because you don't want to take the natural log of a negative number. Usually though, for these kinds of questions, our y value will already be positive, just in context like population or mass. Those values are typically going to be positive, right? So you don't really need the absolute value, but just conceptually, we can just leave it. So the natural log of y will deal with the plus c on the other side of the equal sign here. So this is going to equal, and what is the integral of a constant? So k is our constant with respect to t. So this is going to be kt, and then I'm going to add the plus c, the integral of the plus c. Okay, so question. If you are awake and reviewing, but why is this not k squared over 2? Why is the integral of k dt not k squared over 2? Why did I put kt? Think about that for a minute. Why did I not put k squared over 2? Exactly. Awesome. Very, very good. Exactly. So k is a constant. Pretend it's 3. The integral of 3 with respect to t is 3t, because the derivative of 3t is 3, right? If it were k with respect to k, so if this were integral of k dk, it would be k squared over 2. But k is a constant again, and we're integrating with respect to t. So we have kt plus c. Very good. So we have the natural log of the absolute value of y, or just natural log of y if you prefer, equals kt plus c. Now, a note about constants. If you prefer, you can do this integral. So you have natural log of absolute value of y plus a c1, right? And then on this side you would have like a c2. Now when it comes to integrals and constants in general, we are looking for like a family of functions. So we don't care about these individual constants, right? We can just, if I had the c1 and the c2, I could subtract c1 over here, and c2 minus c1 is still a constant, right? It could be like plus 5 minus 3. It's still a plus c, so I might as well smush them together into a single c. So that's why I don't bother on this side, because we are still trying to keep this very general, and it's unnecessary to keep track of all these little C1s or C2s. But if it helps you visualize what's happening, you can write C1, C2, and when we work this out even further, we'll have like a C3, C4. So if it helps you, you can write that out. Take your time, okay? But in general, unlike for algebra, like in algebra, each variable kind of really matters, right? C1, C2, C3. But here, since we're looking for a family of functions, we don't care if we have two general constants. Then when you subtract them, it's going to be another general constant. So we can just kind of put it as a placeholder. Okay, so now that we have the natural log of the absolute value of y equals kt plus c, we're almost there. We're trying to solve for y here. And so when we have a natural log, that is log base e, right? So we're going to raise both sides. Well, not raise both sides. We're going to take e to the power of both sides, because it's an equal sign. As long as I do the same thing on both sides, it still remains equal. And we're going to do that because we have e to the power of natural log of absolute value of y, which gets rid of it. And at this point, I'm just going to go ahead and get rid of the absolute values again, because population, mass, or whatever else is going to be positive. So e to the natural log of that is going to be y. That's why we're raising everything e to the stuff, because we're just basically going to rewrite this as an exponent equation. Okay, so we have e to this thing, so that's just y equals e to the kt plus my constant c. So now you can see that we have y as a function of t, e is our universal constant, k is our constant of proportionality, c is our general constant, and t is going to be our variable. So this is y as a function of t. Now I'm going to clean this up a little bit to generalize it even further, and all I'm going to do is split this up into e to the kt times e to the c. Remember our exponent rules. If we have the same base raised to two different powers, or two powers, when I multiply them, I keep that base and I add the exponents. So I'm kind of doing the opposite here. I'm pulling out this e to the c, and the reason I'm doing that is so that I can generalize this. E to the c is also a constant, so this would be our c3, and so this is a constant, and so I can just do e to the kt times some kind of constant, which I'm going to clean up, and this is going to officially be our final form for this, is y as a function of t is going to be equal to, and we can write c3, or we can just generalize as c again, e to the kt. Da, 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 da. That is our family of formulas. So c can be any constant. And this is our family of functions. Family of functions that satisfy dy dt equals k times my original function. So let's take a look at that. Okay, so before I erase this, let's take a look again at what we did. We wrote out the main formula, we moved the y term over, the t term over, and we took the integral on both sides, and then we try to isolate the y in terms of t, so we take e to the power of both sides. Then we clean up the constant part a little bit. It comes out in the front, so it's c e to the kt. Y of t is c e to the kt. Very nice. Okay, so let's take a look at this a little bit further and break it down. Alrighty, so now we have a general formula. Y of t equals c e to the kt. Erase this here. Okay, so why is it that this is a solution? So if we take a look at this, this is based on the fact that e to the something when you take the derivative of e to the kt part, or just like e to the t, the derivative of e to the t with respect to t is still e to the t. So when I take the derivative with respect to t here, I'm going to have to use the chain rule just to kind of confirm this. So the first derivative is going to be, I can just pull out that c, that's just a constant anyway. So e to the stuff, the derivative of e to the stuff is going to be e to the stuff. But then you have to chain in this k, right? Because the derivative of kt, if it were just t, it would be e to the t. But because there's a kt, multiplied by the derivative of kt, which is k. And that is this left side. And k times y is going to be k times literally this y. C e to the kt, and these two are indeed the same. C times k, k times c, e to the kt, e to the kt. So both sides are equal now. So that is perfect. So at this point, you can either just use this formula directly. You might see slight variations of this, maybe with the 1 minus some kind of rate, but this is the general formula that we use for most of these kinds of questions. Let me know if you happen to be studying this, by the way, or practicing problems, and you see things written slightly differently. Let us know. It might be helpful for someone else here. And if you have any specific questions that you want to take a look at together, feel free to join our Discord. I think all the information should be down below. But this is the most common formula or way that it's written out for this. So either at this point, sometimes this formula is already written out and we just have to know how to apply it. Sometimes we're only given this, especially for the AP-BC test. It probably is expected, you're probably expected to know how to derive what we just did. So it's probably a good idea to know how to do it, or just practice doing that moving, integral, algebra stuff to get here. But it's good to have seen this. Okay, so we're gonna take a look at this when we do our practice problems. So let's just break this down one more time with this thing. C here, by the way, is our, I didn't even relate this to exponential growth or decay. I'm so silly. But basically C is our initial value, so it might be the initial population, the initial mass. I keep using only those two examples because those are the most common ones, but initial principal, whatever the question says, but it's your initial value. And this is going to be e to the power of, and remember this is with respect to time, so k is a constant, so time, so basically this would be like the value at a particular time. So, it could be 1 day, it could be 10 years, seconds, whatever it is, whatever the units, as long as you're consistent. But basically, if k is greater than 0, you have exponential growth. That makes sense, right? Because if this is e to the, let's say, 3t, then as time increases, so 1, 2, 3, or whatever, 100 years, this e to the something positive is going to grow exponentially large. If k is less than 0, you have a decay situation, because that would have a negative exponent. When you have negative exponents, it's the same thing as making it a fraction, 1 over e to the kt. So if it were e to the negative, well, not kt, but e to like the negative 3t, that would be 1 over e to the 3t. So 1 over e to the absolute value of k times t. So that would mean that as time increases, your value would decrease, which makes it decay. Okay, so in both situations, you can use the same formula, just expect the difference to be just positive or And from here, it's just interpreting your question, setting your variables, writing out like we do with all word problems, writing out all of the information that is given in the question and determining which variables we're solving for. But hopefully with all the equations that we set up and breaking down all the information, we should be able to then mathematically solve for whatever it is that we're looking for. Okay, so let's look at some particular examples here, and I hope that this whiteboard work was helpful, or maybe you're asleep by now. If so, I hope that you're having sweet dreams. If you're feeling drowsy but still can't sleep, I'm giving you permission to just zone out and let go and rest. You deserve it. And you've worked very hard. Squish, your stress away. Okay, so let's take a look. I'm gonna move the camera down and we're going to take a look at these two questions here, which are very common types of problems. Okay, alrighty. See you. Okay, I am ready. Are you ready? Okay, so I am going to go ahead and write out the main formulas that we looked at, just to keep a good framework in the back of our minds. But as usual, I encourage us to not focus so much on memorizing things, especially for, AP Calc and stuff, because we're going to have a lot of different concepts to keep in the back of our minds. So usually, because it's a standardized test, all the information is there, and if anything, it's going to be very, like, they're really trying to lead you to a topic the way that the questions are written. So in this case, though, we're going to just write it out in the back of our minds. So we have, write it out in the back of our minds to keep in the back of our minds. So we have dy dx, and we're going to be flexible, and interpret what that y and x means. And also we'll have y equals c e to the k, x in this case, but time in general. Okay, so we're just going to keep that there, but we're not going to rely on it only. We're going to just run through the derivation again for this question, but just kind of stare at it. So here's our question about exponential growth. So suppose an experimental population of fruit flies grows at a rate proportional to the population. There were 100 flies after the second day and 150 flies after the third day. Approximately how many fruit flies were present at the beginning of the experiment? Okay, so as with all word problems, it's a good idea to just look at all the information that we are given, and let's pretend we didn't even know that this was an exponential growth kind of question. So how would we really determine that in the first place? Well, besides having this on the side, we have the first line. Suppose an experimental population of fruit flies grows at a rate proportional to the population. So we have an experimental population, fruit flies, grows at a rate. So the population is growing at a rate proportional. So this is the varies directly or is directly proportional to the population at a given time. So right there, if I have P of t, so let P of t equal the population of fruit flies at time t. So it's a function of t because as t changes, the population is going to change. For instance, after the second day, we have 100 flies. After the third day, we have 150 flies. So if we let p be a function of t, we can just do pt, p of t. So that's going to be our y, actually. But let's say, again, we don't know this formula. Let's just say we have a population. It changes and it grows at a rate proportional to the population. So the rate of change is going to be dp dt. It's an instantaneous rate of change at a particular time, and this is, in general, it's a function. So dp dt is proportional, which we'll assume is directly proportional. So we'll have our k to the population. So p, or p of t. So now we have our general formula. Now, the test might, on the test, if this is like a free response question, you might have to carry out that same derivation that we did on the whiteboard. So we'll run through it kind of quickly since we already did this. But this is our general formula again, right? The dy dx equals k times y. So we're going to separate this. So we have dp over p equals k dt. Then you go ahead and take the integral on both sides. Shoop, shoop. Get natural log of p, and population of fruit flies is going to be positive, so no need for absolute value. You might want to write that like on the side, like population, just to be safe. It's greater than 0. So this would be equal to kt plus c, and then raise e to the power of both sides. Doop, 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 doop. E to the natural log of p is going to be p. This is going to be e to the kt plus c. We're going to split that up to kt times e to the c. E to the c is a constant, so this is going to be c e to the kt. So we just derived our formula again, and of course the c is still not the c, it's just a general constant. But now we have a general function, p of t equals c e to the kt. So we derived it ourselves. And now we just want to plug in the information given, which is that there were 100 after the second day and 150 after the third day. So this is going to mean that p of 2, so our units for t is going to be days in this question. So p of 2 is equal to 100, and p of 2 is going to just be where t is 2. So this is equal to c, which is our initial value, which is actually what we're solving for, approximately how many fruit flies were present at the beginning. So we're looking for c, our initial value, but we have 100 equals c e to the k times 2. P of 2 is just plugging in t is 2 into our formula. So we have one equation there. K2 is going to be 2k. And then we have p of 3. After the third day, we have 150. So p of 3 equals 150, which equals c e to the k3, or 3k. So now we have two equations with two variables. So let's clean that up. C e to the 2k, 150 equals c e to the 3k. Looking great. So we have two variables, c and k, and we have two equations. So we can now solve this however we want. If you want to substitute, you can solve for c and then substitute and then work this out. What I'm going to do though is I noticed that I have c times both of these here and here. So I'm going to actually divide this second equation by the first so that I have 150 over 100 equals c e to the 3k over c e to the 2k, because now the c's cancel, and this is one of our exponent rules. It's that we have e to the stuff divided by e to the stuff, so I do e to the stuff minus other stuff. So this is e to the k. So that means 150 divided by 100 is going to be 1.5. Just move the decimal over. Don't get too dependent on your calculator there. So it's 1.5 equals e to the k, which means that I can take the natural log on both sides and get that k equals natural log of 1.5. Natural log, again, being log base e, right? So here we can type this into our scientific calculator and get a value. But let's remind ourselves what we're actually looking for. We are looking for not k, we are looking for c, the initial value. So if we just look at these two formulas here, which is what we're trying to focus on and solve, we have k and c. So if we already know what k is, we can just pick whichever formula we want to then solve for the c value. So we can substitute either or. So let's just go ahead and pick the first one, why not? So we would have 100 equals c e to the 2k, where k is natural log of 1.5. We can solve for c here. We'd have c equals 100 over, we just divide all of this stuff over, 100 over e to the 2 natural log of 1.5. At this point, you can go ahead and plug this all into your calculator, and we're just going to round it to a reasonable value because we're trying to approximate how many fruit flies were present at the beginning. So we can just round, or if you're comfortable with your exponent rules, you can actually mess around with this further, do 1.5 squared, get rid of that, but it's not necessary. Okay, so now let's take a look at the other one. Let me know if you have any questions about this, by the way. So this is going to be our decay question. Oh yeah, so note that in this last question we got k is natural log of 1.5. That's going to be positive, because this is exponential growth. So let's actually type in what the natural log of 1.5 looks like. 0.40546. So yes, indeed, that would make it exponential growth. So now we have an exponential decay question. So let's read the question. The polonium isotope PO214 has a half-life of about 1.6 times 10 to the negative 4 seconds. How long would it take for a sample that has a mass of 20 milligrams to decay to 1 milligram? Okay, so in this question it literally says decay, but what gives us the clue that it's going to be exponential decay is this idea of half-life. So this polonium isotope PO214 has a half-life of about 1.6 times 10 to the negative 4 seconds. So that means if I were to start with 20 milligrams here, 20 milligrams of PO214, it would take 1.6 times 10 to the negative 4 seconds to have that amount. So to 10 mg, 20 to 10, it would take 1.6 times 10 to the negative 4 seconds. So super fast. Okay. And then to have it again, so half of 10 would be 5, and half that again would be 2.5. Half that again would be, 1.25, right? And then half that again would be about 0.67. 0.75. It doesn't have to be exact here, but the idea is that to have each time, it would take another 1.6 times 10 to the negative 4 seconds, another 1.6 times 10 to the negative 4. So we can actually estimate our answer here without even calculating it, just to make sure we're in the right ballpark. But basically, it takes 1.6 times 10 to the negative 4 to have once, again. So another 1.6 times 10 to the negative 4 will give us 1.25, and then not quite the next one because we only want one, so not quite this. So it's going to be a little bit more than 4 times 1.6 times 10 to the negative 4, which is 6.4, right? 64. So 6.4 times 10 to the negative 4 seconds. So this is just a guess, just to make sure. So it's going to be a little more than 6.4 times 10 to the negative 4, okay? Because it's going to be at 1.25 at 6.4 times 10 to the negative 4 seconds. So we want it to decay a little bit more, but not quite a full half more. So now we're going to actually calculate the exact time. So let's take a look at that. So now we know that it is an exponential decay without having to write varies proportionally or is directly proportional. But the idea of half-life and the fact that it says decay kind of makes us want to start with the formula. In this case, it's going to be mass. So I might as well let m of t be the mass of PO214 at time t. So what we do know is that our initial value is 20. So remember, we have mass of t equals CE to the KT. C is my initial value here. So we have 20e to the KT. And now we just want to fill in whatever information we're given and figure out what we're looking for. So we do know that the half-life is 1.6 times 10 to the negative 4, which means that if I put in from 20 to 10, if I halved it once, it would be at 10 milligrams after 1.6 times 10 to the negative 4 seconds. So K times 1.6 times 10 to the negative 4. Okay, so this is putting, in other words, after 1.6 times 10 to the negative 4 seconds, my initial 20 will now be 10. So I'm plugging in that information so that I can then solve for K. So here I'm going to divide by 20. So that's going to be 1/2 equals e to the K times 1.6 times 10 to the negative 4. I'm going to take natural log on both sides just to get rid of the e to the stuff. I have natural log of 0.5, half is 0.5, equals K times 1.6 times 10 to the negative 4. Then I'm going to go ahead and divide this whole thing over to solve for K. So K equals natural log of 0.5 over 1.6 times 10 to the negative 4. Good. Now we can plug this into our calculator to get an approximate amount, or we can just leave it as is until the very end so that we can be more precise. But we're just going to have to keep copying this over and over and over. That's okay. So then the question is, K is our constant, so it is a constant in our entire function here. So our function will be 20 times e to this stuff, t. But we want to know how long it takes to get to 1. So we're solving for t t now. So we want 1 equals 20 e to the k, which is still this. It's a constant throughout the entire function. So ln of 0.5 over 1.6 times 10 to the negative 4 time. And we're solving for that time. So here we just solve for this value. We move the 20 over. And at this point, we know we're going to take the natural log on both sides, but I guess we can just write it out. So e to the ln of 0.5 over 1.6 times 10 to the negative 4t. Unfortunately, we can't simplify this really because we have a natural log on the top, but we have stuff on the bottom, so we can't really mess around with this much, but it's e to the power of all this stuff. So we're going to take the natural log of that, and then we're going to go ahead and write all of it out. 1.6 times 10 to the negative 4t, and we're going to solve for t. So we're going to divide this over. So since we're not approximating along the way, it's going to be really long, but don't worry, this is just all algebra, right? Don't get scared off by all these numbers. Just be patient one at a time and do the steps that you know. Multiply if it was a divide, divide if it was a multiply, just scooch everything over. You've got it, okay? So t is 1.6 times 10 to the negative 4 times the natural log of 1 over 20 all over the natural log of 0.5. And this we are going to type into our calculator to get approximate time, and hopefully it's about what we estimated, 6.4 times 10 to the negative 4. A little bit more than that. So let's see if we are in the right ballpark. So we have 1.6 times 10 to the power of negative 4, okay, times natural log of 1 over 20, and then that whole thing divided by the natural log of 0.5. Okay, so we have 6.915 times 10 to the negative 4. That's excellent. 6.915 times 10 to the negative 4 seconds. Remember, our unit is going to be time, so that's going to be in seconds. So you can round that to 2 decimal places, 6.91 or 6.92, depending on how you like to round things. There are different rules. Some people say if it's odd or even or whatever, but I'd like to round up if it's 5 or above. So 6.92 times 10 to the negative 4 seconds, which is a little bit more than our 6.4 times 10 to the negative 4 seconds. So it looks like we're on the right track. But that's really it. So this is an example of plugging in our main formula, but understanding what half-life means. So half-life is the amount of time for the mass to literally halve. So then we solved for k to make that work, and then the question is to find how long it takes to go from 20 to 1. So we plug that exact k into the general formula again, because it's going to be the same k for this question. So we just, now that we solved for k, we plug it into the general equation and put in our 1 to find what that time is. Then the rest is just a bit of algebra, okay? Okay, so let me know if you have any questions. Again, this k is going to be negative. Natural log of 0.5 should be negative. This bottom part is positive, so a negative divided by a positive, negative 0.693. So that's going to be a negative k, which is what tells us it's a decay question, or it's consistent. So let me know if you have any questions. Traffic noises and background noises are a little bit loud today. I'm going to do my best to edit out what I can, but hopefully it's not distracting or anything. I hope that you are relaxed and resting this. Maybe it's helpful. I hope it's helpful. And I will see you around for more math very, very soon. If you have any topic requests, let me know. Just directly message me anywhere, comment down below. If you have any affirmations, please check out my community tab, because that video will be, I'll be making that soon, and I would love to share more love and positivity. And I will see you around. Like I said,